Oh, what? You wanna hang out? Come up. Come. Hey, everyone. Yeah. So I was sort of dealing. Wait. Can I change this thing? I was sort of dealing with my cat Yan over here, who has decided they wanna hang out with us. So I wonder if I can change the. I wonder if I can change the logo that's on my face. Yeah, cool. Let's also just get this in here, and then I should be able to start now. Yeah, that's it. Cool. Okay, cool. So let's do some stuff today. I think what we're gonna do today is I considered how to do this, and I considered just jumping straight to the code and starting it. But it's one of those things where the actual implementation code for this is going to be very little, because we'll basically be doing some sort of vector multiplication and or convolving if that's the word that's more comfortable for you. I considered that, but then I thought it's not the kind of thing that I wanted to do. I'm doing these streams to kind of show what really working on these things is, and I think it would be prudent if I just went through the first, if I went through step by step and I did it. So we want to sort of what we eventually want to do is we want to measure or rather detect loud noises, like say a clap, detect a clap with a microphone, and that is on the application that we're building. So this guy, this it's an NRF 52840 with a microphone attached on the side. And what we want to do is basically detect when audio above a certain amplitude is measured. And in order to do that, we're going to use something that's called amplitude thresholds. Amplitude threshold or amplitude thresholding. Amplitude threshold. Yeah, something like that. So this is going to enable us, we're going to set a threshold or a number of thresholds, and then based on those thresholds we're going to see if we'll see if the amplitude of the signal that we are analyzing crosses that. And if indeed the amplitude of the signal crosses that, then we can classify that as a loud noise. And we'll start by detecting something like a loud noise, and then we'll go and detect something like speech, and then so on, and we'll build up slowly till to a point where we can basically detect a word or some sort of wake word or something. That's how you end up building a system like Hey Google or Hey Siri. My phone's gonna do something, I don't want it to do something. So basically that's what we're going to do. And I think today is gonna be sort of we'll do a small discussion of how this works, and what are the things that one builds into, and what concepts do you sort of use when you're building this. And as we build up that, then probably at the end of the session we'll end up using a web tool or some sort of thing to design a filter that we're now going to start applying in the next few sessions. So this is going to be part one of a filtering session that's probably going to be, I think, I want to say 2 parts, but based on experience I think it's going to be a part of a 3 or 4 part series where we go around and we basically implement filtering on an audio signal, and see why we're building that filter. So what are filters? What are digital filters? This sort of presupposes that one understands what digital signal processing is, and I think I've covered it in a previous thing. But digital signal processing is it really is what it sounds like. It's doing some sort of analytical work, or however way you want to put it, or analytical or changing work, or transforming signals that are digital in nature. So digital in nature, which means they're discrete signals. These are signals that your computer can understand. Okay, as opposed to continuous signals, which are signals that are happen in the world. Something like sound. Continuous signals have infinite values. They can go infinitely up, infinitely down, and then they have the continuum. The continuum from one, like digital is sort of like 1 or 0, so it could be high or low, and then there's all of that middle. Like the other day we were dealing with sigmoid neurons, and we talked about what is a sigmoid neuron operates on floats, and then there's a perceptron that operates on 1s or 0s, on a binary input. So digital signals are of a binary nature, and then continuous signals are of a continuous nature. So like contiguous or continuous nature, basically they go like, instead of going 1 to 2, it's like 1.0, I mean 1.0001, 1.002, 1.003, 1.004, and that's why you can get 4096 values from a 12-bit ADC, sort of like that. There's going to be a lot of context mixing in this session, but okay, so that's sort of what filters that's what DSP is. Digital filters are a feature or a pattern or a functionality that is implemented in DSP, and basically what this feature or functionality allows us to do is it allows us to do something like removing some parts of a signal that you don't want, or maybe combining two signals. Maybe you can have like a signal that is 50 hertz, and then you have another signal that is 100 hertz, and then you want to combine them all into one signal and send them over some, let's say, radio thing, and then on the other side you want some radio to receive it and differentiate these two signals and do something with them. And then also this is used extensively in embedded systems. This is used extensively in computed systems. You're going to encounter this when you do audio work. You're going to encounter this when you do image signal processing. You're going to encounter this when you do networking work, and whenever you're doing something that is making something. Imagine when you need to convert a signal to like a raw value, send it or something, and then receive it on the other side. You're going to do some sort of signal processing, and it's going to be the analog or digital. And since we do a lot of work on digital computers, most likely it's going to be a digital signal. So let me come to my blog so I can start scrolling and probably leave that running. Okay, cool. So the link to this is on the is below, is in the description. That's below. But if you do want it, it's over there on the screen. But I'll add it to the description shortly and save it so that everyone can have access to it. Yeah, it's there. Okay, so let's keep going. So digital filters are going to accept signals into them, and a signal is basically a collection of samples, if that makes any sense. So, hi Bartolomeo. A signal is going to be a collection of single samples that are taken at discrete times. So let's think about something like you want to check if the light is on for the next 20 seconds. Okay, and each second is when you check. Okay, so you would have, if you checked every second for the next 20 seconds, you would have 20 samples. And then your values would be like light on, light off, light on, light off, light on, light off, light on, light off, or light on, or light off, whichever values you want. And that collection of that bits of information at this point in time, this is what the signal was doing. The amplitude of the signal was here. It was high or it was low. That is what is called a signal. So inputs into a digital filter will be a signal. And a signal is usually a sequence of numbers. Each number is a sample. So a signal is made up of a number of samples. Okay? And you'll find different ways of defining this all over the place. And maybe I'm not being very mathematically rigorous right now, but what I want to do is convey this in a simple way that you can use, okay? That you can use whatever you're doing, in whatever you're doing. I'm not trying to get you to do audio filtering. What I'm trying to get us to understand is what signals are, what digital filters are, and how to use them. So, cool. Okay, cool. So, inputs to a digital signal will be digital filter will be a signal, which is basically a group of numbers, and they're going to be in our particular problem, they're going to be equally spaced in time, so they're going to be in the time domain, and this is due to something called a fixed sample frequency. And that means, as I started when I was talking about, if you're going to check the state of the light for the next 20 seconds, you're going to check each second, so your sampling frequency is each second, basically. So in essence, that's just collecting where the signal is at certain points in time, and then we call that a signal, or amplitudes of this thing at certain points in time, and then we call them a signal. And then we use a filter to apply what is called a frequency response. And the reason I'm thinking about it, the reason it's called a frequency response is because when you're in a digital computer, it's easier to reason about things in frequencies rather than in some other formula. Okay, but you can't use other things like you can't use other measurements ways of doing it. But a frequency response is something that takes a certain frequency, and based on that frequency, it decides what to do. Okay, so let's talk about something like a low pass. That's something you'll hear as you go, or a low pass, or a band pass, or a high pass. A low pass frequency response will let low frequencies go through, and then higher frequencies will be prevented from going through. And that happens, that basically gives you some sort of like smoothing out. But also the opposite might be true. You know, you could want higher frequencies to stay and lowers to stop. You could do that, something of the sort. And that fact is called a frequency response. And then when you run signals through a frequency, through a digital filter, this frequency response, what you will also get is, on the other side, you will get probably another signal of equal size or equal, so if it's n numbers, n elements, n samples in the frequency, there's a lot of words and I'm mixing them up. If there's n samples in the signal, you run it through a filter, you get n samples out of the filter. But this is not always the case. You might get some things that destroy samples, and something, I think there's a decimation filter or something like that, and it made drop elements of the signal, and then you might get a different sized one. So this is a very wide and varied field. It's not something small that is finite or it works like this. You can find very many different, and at some point you get so good you start combining filters, and you could make responses that are a different way, basically, is what I mean. So whenever we need to make a filter, we need to decide what that filter will do to our signal. Okay, and we've sort of spoken about this in a minute before, and we talked about like a frequency response. It will do something based on the frequency that it is given. So we need to design what it will do. Okay, so let's consider something very sort of let's consider something very like let's make a funny example that we can talk through quickly, and then we'll go through forwards. So we make a frequency response. This is how this the filter deals with frequencies in our signal. Okay, and then once we get that frequency response, we pass it through the inverse of a Fourier transform, and that gives us something that is called an impulse response. And an impulse response is a set of values that we can apply on a signal, and then that will do that. Basically, it helps us to do the filter itself. Let's talk about something practical, and then we can start seeing how this takes shape. So let's introduce something called as a window sync method, and this has two parts of it. So let's say we want to implement some sort of low pass filter that allows frequencies that are under 50 hertz. So if you're 50 hertz to go through, and then frequencies that are above 50 hertz to not go through. So the formula would be sort of this. You would be passing in frequencies of certain amount, and if the frequency is under 50 hertz, it would be let go through. So you would return a 1, and you would let the value of the frequency go through. But if the frequency is is more than 50 hertz, you would return a 0, or something of the sort, where you would not let it. You basically would set it to 0. So there was no frequencies. There was no frequency. There was no. What? There's a word that's missing here. There's no sample there. Basically, you would make that sample disappear by setting it to 0. So you make it. You're basically smooth. You're choosing the ones you want, and then assume you had. Let's think about it. Assume you had 5 samples. 45, 46, 52, 58, 49. The 45, 46, 52, 58, 49. So that's 5. And then what our thing would do is it would say 45, it's less than 50. Yes, pass. 48, less than 50. Yes, pass. 53, more than 50. No, don't pass. 54, more than 50. No, don't pass. 45 at the end, less than 50. Yes, pass. So we have this thing that takes in frequencies and decides what to do with them. Now, once you have that, you need to apply this value, this 50 hertz border to we need to apply the inverse of the Fourier transform to it. And this also sounds very very complicated, and I don't want to go into the calculus of explaining why it works, because that becomes a longer thing, although I don't mind doing it, but that becomes a much longer series, and that someone could learn by themselves. However, it sounds scary, but it's not. The way an inverse Fourier transform works is it goes from negative infinity to positive infinity, and then for each of those, you remember the continuous signals, continuous samples that I was talking about, 1, 1.001, 1.002. For all of this super small increments, it applies an integral, and an integral is you apply a formula, and then you add up the results of those formula, and then you get some sort of value at the end, basically. However, if you do this, you end up with this continuum that is quite huge. You would be surprised by the amount of data you can produce if you went with it's sort of like what is the difference between a Gaussian distribution and like a digital distribution. So basically, you're accounting for very fine little steps. But if you account for these very fine little steps, the data that you have to deal with grows and becomes so much, and you can't deal with it. Okay. So how do we deal with this? Okay. So if you plot this for an ideal low-pass filter, an ideal low-pass filter is something that is, as you've designed it, it will work that way. but rarely are we dealing with ideal situations. We usually want to deal with realized situations, which is real situations where we're dealing with continuums that happens in the normal world. Okay. Anyways, let's start. So, applying the Fourier transform to the frequency response that we developed earlier, the inverse of the Fourier transform into the frequency response that we developed earlier, gives us something that is called a sinc function. But then the sinc function, like normal or like continuous aspects, it lives on a scale that we sometimes cannot replicate. And this is because it has negative values, which we can't really apply this. And the proper academic term here is causality. This signal, this function becomes non-causal. And non-causal means it sort of depends on it depends on inputs from the future. Okay? And then you have causal functions which depend on inputs from the present and the past. And then you have some class of functions that are also called anti-causal functions, which depend entirely on inputs from the future. Okay? But what we want to make this so that it depends on inputs from the present and the past only. So we want to make it causal. And an easy way of doing this is to shift this whole thing to the right. If we shift it all to the right, we basically remove all the negative values of it, and it comes to the right. So that's the first fix that we need to apply to the sinc function. The second fix that we need to apply to the sinc function is this little tails over here, they sort of seem to get to 0. Yeah, these ones, they sort of seem to get to 0. But in reality, because remember this function is developed for negative infinity and positive infinity. And remember, we're dealing with super, super small increments. So this tails over here, they don't really get to 0, they just keep getting smaller and smaller, closer to 0 as the thing goes. So what happens is the sinc functions happens to be infinite. Okay, and what we want is actually a finite. Remember, finite input impulse response. We want a finite impulse response, not an infinite one. And an infinite one, you use it in the IIR filters, which is the inverse of this filter that we're talking about today. So the second thing we do, in order for us to actually contain this thing in numbers that we can use, is we truncate it somewhere. Okay, so now once we truncate it, like if you move, we shift it to the right, which is this image that's coming up. We shift it to the right, and then we truncate this one so that we actually end up at 0. Okay, so the reason it's called a finite impulse response is because it always ends at 0. So you want it to always end at 0 on both sides. You want it to always end at 0. So you have to truncate it. Okay, we have to truncate this sinc function that we've gotten from the continuous realm into our discrete realm. We have to truncate it so that it starts at 0 and it ends at 0 and it does its own thing, and then we have it. Okay, so. And then the other part of this is this sinc functions, it just gives us values that are still in the time domain. So it's still continuous. But in our computer, we're going to do stuff in something discrete. So we need to discretize it, which means moving it from time domain to something like the frequency domain, which is what we're dealing with right now. Okay? If we take these 3 steps, the first step is it's non-causal. We need to make it causal by sliding it to the right, removing the negative ones, and then the tails, they're infinite. If we chop them, truncate them so that they're finite, so that they end and they start at 0, and then the third part is we discretize it. we end up with something that looks like this. Okay, so it's the same, it's really the same shape, okay, but it's been moved this way so that this is just this hump becomes just a little bit after 0, and then we truncate it so that it always ends at 0. Okay, so this is what it ends at 0, and then it moves, we shift it to the right. And this image, by the way, is from a video by Phil's lab. I really looked for an image like this and I couldn't sketch it, so I went and got a screenshot from there. However, doing this does fix the 3 problems for us, but it causes another problem. And whenever we're applying this in audio, we will leave it in so that we can feel it. When we get a filter like this, because we're dealing with a continuous signal in the first place, what happens is we cause this ripples. It's called the Gibbs phenomenon. Gibbs phenomenon. I'm going to pause there, do a couple of questions. Yeah, so we call this the Gibbs phenomenon. And the Gibbs phenomenon is, it's the oscillator. It's kind of went backwards because this is now defining it in the thing that I've just defined. It's like they're saying here, it's the oscillatory behavior of the Fourier transform of the Fourier series of a piecewise continuously differentiable periodic function. But what I'm saying is this ripples. You see this ripples? This is what this is what the truncation causes. The truncation of the impulse response causes, and we want to avoid these ripples. So how do we do that? There's a couple of confusing, well, for me it was quite confusing in the first place. There's a couple of confusing concepts that I had to do. So this brings us to our first encounter with something called windowing, or a window function. So there's 2 places we're going to do. There's a sliding window that we're going to apply at the end of all of this. Okay, this is going to be applied to the data itself. But then we still need to apply some sort of window function to smooth out this, you see, to smooth out this these ripples so that they're not happening. And there should be solutions. There are never negative, but there should be something here that says, but we're basically going to apply something that is called a window function. And a window function basically, how do I say this? A window function basically removes these discontinuities, removes these little ripples that we have introduced by doing a truncation on it. And it's basically a smoothing function. But in this respect, this window function that we're looking at right now is a window function that is applied on the filter itself, not a window function that is applied on the data. That will come later, okay? And this is this sliding window is a bit misleading. I should change this, because now as I'm reading this back in here, I'm realizing I'm referring to the sliding window, but the sliding window really refers to, let's change that. It's fine, let's change that. We shouldn't have that in there. So that is not how it becomes a sliding window thing. That is genuinely not how it becomes a sliding window. Sliding. And hence we have a window, a windowed FIR filter. Okay, cool. So the windowing we apply to the filter itself. This window that we are talking about, we apply. So the window sync method that is inside building a filter, we apply that window to the filter itself, so that the filter does not cause the ripples. Okay. Later, we will apply something called a sliding window, and this sliding window will enable us to smooth out the data, or rather the samples that we are filtering themselves, rather than the filter. Okay, cool. So So what is a key factor when we are sampling frequencies? When we're designing filters for sampling frequencies, we need to know the sampling frequency. That way we can define a filter that works with the Nyquist limit. Is it a Nyquist limit or a Nyquist theorem? So this Nyquist theorem, yeah, the Nyquist theorem, which means you can only do proper sampling if you sample at twice the rate that you're going to need to filter at. So the Nyquist channel sampling theorem is an essential principle for digital signal processing, linking the frequency range of a signal and the sample rate required to avoid a distortion called aliasing. Again, something. You will some words here you've already encountered. If you've ever heard of an anti-aliasing filter, or if you've ever looked at a design or a block diagram for an analog to digital converter, ADC block diagram. Actually, DSP guide. Let's look at something quickly before we go on. The book by chapters, analog to digital converters. If you've ever looked at this, ADC, quantization. So you'll have something. Your ADC is going to have analog input, analog filters for data conversion. Yeah, see, you're going to have some filters, and there's going to be something anti-alias filter here, and a reconstruction filter. So aliasing and anti-aliasing filters, and you use this when you're kind of saving you're moving from either digital to analog or analog to digital. And these are also filters that we can learn about, but we'll work with them later. I don't know if I'm gonna actually cover analog filters. Okay, the other part is you want to know how many coefficients you want to put in your filter. So this is a filter length. A longer filter basically makes it so that you have more work for your signal processing system, but enables you to have a higher resolution. So your steps can be smaller. Okay, your steps can be smaller. Basically, you have a higher resolution, and then you have a frequency response. What do you want your filter to do? This is also a factor when you're designing a filter. So you want to do a low pass? Do you want to do a high pass? Do you want to do a band pass? Where you want to do like not low pass, not band, not high pass, but you want this filters, you want signals in between here or something. And there's a lot more of that. And then the windowing function for your filter itself. So it's something like humming or hunning or Blackman. There's quite a few of this. It's mathematics. So there's a lot of this. They've been discovered. They're quite well known and such. Okay. And then time domain properties. So you want to know properties that are going to sort of affect your signal. What is the rise time? What is the wait time? And things of so how long do you need to wait before you do this, before you do that? And all of these are factors that you're going to that your filter is going to use. Okay. Given that, let's actually design some sort of filter. And the way we're going to do it is we're going to design a filter based on using a tool I found. Well, it's been out there for a long time. So there's this tool. It's called T-filter. And we can use this to design some sort of filter. So let's ask Google some questions, and then we can do some filters. Frequency of loud clap sound. In the meanwhile, if anyone has any questions, please. Yeah. let's look at this. Cura. What is the frequency of hand clap? Well, there are two ways to think about it. Hand clapping ranges in repetition, frequency from slow to about 5 hertz. So what I want to do is just, yeah, let's actually use those. Let's use those. Yeah? Let's use those. Let's just use those and assume that they are correct. So let's say we want anything over 1,500 hertz to pass. Okay, so we want to detect a clap. Okay, a clap is sharp and it's high frequency. So we basically don't want a low frequency. Okay, so we want to stop low frequencies from going through, number one. And then we want to also, we don't want to leave it to the top, basically, because of Nyquist's theorem, if we are sampling at 44,100 hertz, we are only sampling all the way to 22,500. We're able to use only half of that. So we don't want to leave it all the way to the top, because there might be something like some background electrical noise that's like some loud hiss in the background. So we want to leave that out. So we want to detect some sort of clap. Okay, and sorry for if you're using headphones, sorry for that. And we've decided that the frequency of the clap itself is going to be something like 2 kilohertz to, let's say, 6 kilohertz. Okay, so let's use this and let's design our filter. So I'm going to remove this 2 here, and then I'm going to add a stop band. So 0 to 1,500, let's say. I'm going to stop that, and I'm going to put no gain on that, and I'm going to leave the ripple as it is. Okay, and then I'm going to design a passband. So if audio goes through this, the thing that we will receive on the other side is basically it will remove everything that is not what we want, and then it will keep what we want. Okay, cool. And then let's add a passband. Yeah, let's add a passband, and our passband will start at something like 2,000 hertz, and then let's keep it all the way to something like 6,000 hertz, and then let's leave 1 as a gain for it, so that's basically no gain. And then this, I think I'll put the ripple to 0.5. Okay, and all of these are things that they're in textbooks and research pieces and stuff, and the more you do this, the more you get familiar with this, the more you gain little bits of information here and there, and then as you build them, as you get them, you're able to do stuff with them. Okay, cool. And then we said our sampling frequency is 44,100, and I'm getting this one from the 44,100. And then desired taps, this is going to be the length of the filter, so the coefficients in the filter. Okay, so in here we'll put something like 50. I think 50 should be good. Okay, in the old days, you would have to pull out calculus books, all of your notes from uni, and try and write this and try and do proofs by hand so that you can do this, or rather apply the inverse and then you would get it. But we have software that can do this for us. Let's stand on the shoulders of giants. Let's design the filter. Cool. Ooh, overlapping bands. 1,000 hertz, so we said from 2,000 hertz. Okay, sorry. Yeah, so our bands are overlapping. That's cool, actually. From 2,000 hertz to 6,000 hertz. Okay, cool. So stop everything from 0 to 1,000 hertz. Let everything that goes from 2,000 hertz to 6,000 hertz pass. So cool. So let's do design filter. All right, awesome. So this is gain versus frequency. That's fine. That's okay. We don't really want to use that. This is the impulse response. Here we go. Look, this is going to look eerily similar to our to the image that we have of our actual, yeah, it looks like this, but it's not this because this has negatives. You see, this does not have a negative here. Okay, so this does not have a negative here. This starts from 0. Cool. So actually what this is, this has already been shifted to the right. Okay, this has been shifted to the right. They've already done the work for us. This has been shifted to the right, and since this point, you see this point is a 0 and this point is a 0. It starts as a 0 and it eventually goes back to 0. That is what makes it a finite impulse response. Okay, so look, it starts at 0, goes all the way and ends up at 0. So it's done those two things that we needed to do. It's basically done this. It's shifted it, okay, and then it's done the truncation so that it ends up at 0, and then because it does it's doing it in the background. The discretization has also been done. Okay, cool. So what does that give us? It gives us this filter, or rather gives us this impulse response, and we can get this, we can put this in our code by going to the source code, and this is the filter tabs that we want. Okay, cool. So with these tabs, tabs are coefficients. Coefficients are sometimes denoted as H. It's tabs, coefficients, filter length, filter n. These are all concepts that refer to the same thing. So now this gives us a filter that we can now go back and use in our actual data by ourselves. And this will sort of work. The reason it works is because there's a way of relating convolving in mathematical terms in continuous, basically calculus, and convolving in continuous stuff is basically, which is a multiplication followed by an integral, is in discrete terms is a multiplication followed by a summation. Okay, so summation on this side, and on the other side we have convolving. They're the same thing. When you move between domains, like a frequency domain to a frequency domain to a time domain, in the time domain it's convolving, in the frequency domain is multiplication, and that's basically the translation. And if you go down and dig through and do the proofs in the math, you will find that this actually does do the thing. So that is how we go from we need to do something with a signal. This is what we want done to the signal, to designing the thing that does the thing to our signal. And the thing that does the thing to our signal is called a filter. So you have a filter, you have a signal, you want to do something to that signal. This is how we design the filter for it. Those are the factors that you take into account, and those are the top factors that you build out. Now, the next time we meet up, what we're going to do is we're going to take this array that we've taken, and we're going to take it into our code, and we're going to apply this filter to our signals so that we can actually get good, we can filter out the signals that we don't want. And then after we apply this to a signal, we're going to watch that, we're going to apply what is called an hysterectic. What? That always gets me every time. Hysterectic. I should make it say it. Not a problem. Not a problem even if it's not full, but it's easier to see. Hysteresis. How do I say it?
Hysteresis.
Sorry. You guys can probably hear it. I can't hear it. Okay, how do I say? Hysteresis. Anyways. Yeah, so after we've filtered our signal and we know we're getting the signal that we want, we're going to use hysteresis to determine that a clap has occurred and we are sensing the one individual clap, because hysteresis, as I explained last time, is a dependency on a signal on its history. Okay, cool. So next time we meet up, we're going to be doing this in code, and we're going to be applying the things that we've learned in this session there. I'm gonna do something like, is there any questions? I feel like that was not very clear. I feel like I could have been clearer, but you know, this is what you do. You have to do what you can every day and see. Are there any questions on this? Anyone with questions? Let me check on WhatsApp as well and on Discord. No questions on WhatsApp. No questions on Discord. And I see no questions on YouTube. Okay, so thank you so much for hanging out with me today. This has been a cool session. It's been very involving, I'd say, because I'm trying to summarize stuff very quickly that took me quite a long time to learn and that I'm still actually going through. So thank you so much for hanging out with me today. That's been amazing. Check you out later, soon, tomorrow when we do some code on this. Cheers. Thank you, everyone. Thanks for coming.